First of all, I'd like to thank the organizers for the invitation to talk here. Looks like it's going to be a very interesting conference. And also my collaborators. This work mostly would be work in collaboration with Howard Wiseman, but also some of it has to do with a previous work with Ray Lau from Oxford. This will be a very conceptual talk, quite philosophical, really. It's about a question that Jan was asking in the introductory talk, which is about how can we conciliate between the operationalist and the realist point of view. And my conclusion really is going to be that both operationalists and realists have something to gain from looking at the other's point of view on interpretation of Bell's theorem. Actually, 2 days ago, I was listening to a podcast on Radio National, the Australian Radio National, and it's called Philosopher's Zone. So they were talking about a guy who's a philosopher who went around the world talking to different groups of people, very sort of divided groups like the Israelis and Palestinians, or people at very different levels in the social inequality division in Brazil, or Native Americans and non-Native Americans. And he got them together in a room and to talk about philosophy and to question their assumptions about the world and how they see each other. And he found that by the end, many of the times, he could sort of bridge a little bit of the gap between those people. And then I thought, well, if that could be done for, say, Israelis and Palestinians, so how about the realists and the operationalists? And I thought, if only it was that easy. I think, there's very deep-seated intuitions here. But hopefully, by the end of the talk, at least I can convince you that at least trying to think about, a sort of an opposite point of view can be and has been helpful in developing our understanding of quantum theory. And also, it's a very timely moment to talk about this because, as you probably know, recently there's been an experiment that's shown a loophole-free violation of a Bell inequality. It's a great experiment, very important development, but also it shows that it's still, even 50 years after Bell, we haven't quite come to understand what does that experiment is telling us. What do these authors actually think that the experiment is telling us? So that we see that in the paper, they say, for more than 80 years, the counterintuitive predictions of quantum theory have stimulated debate about the nature of reality. In his seminal work, John Bell proved that no theory of nature that obeyed locality and realism can reproduce all the predictions of quantum theory. Many of you might think that these are actually probably bad words to describe what Bell tried to prove. And that's going to be part of this talk, will be what do we mean by locality, what do we mean by realism, or at least what possible meanings can there be. And all of this debate can be sort of framed in terms of a divide between these operationalist and the realist camps. And here I'll use Reinhard Werner and Tim Maudling as sort of the archetypal operationist and realist, respectively, although they may or may not agree with that characterization. But just using them because recently in this issue on 50 years of Bell's theorem, they had a very heated debate that also spilled to the archive about the meaning of Bell's theorem. So Werner, paraphrasing what he would have said about it, he would say that Bell's theorem has two assumptions. The first is locality. Quantum mechanics respects this. The second is something else, which I call classicality, but which is also called determinism or realism. Clearly, it is this that we should abandon. Locality is here to stay. Maudling, on the other hand, would say something like, Bell's theorem uses only one assumption, locality, or local causality, as Bell sometimes called it. Standard quantum mechanics is non-local. Bell's theorem proves that the world itself is non-local. So now, I don't think this is supposed to be defined, resolved by a vote, but I'm just interested to see what are the people's different inclinations here, what kind of sympathies would you have. So can I have, say, a show of hands if you sympathize more with the operationist view represented here by Werner? Not many, okay. All right, okay. If you sympathize more with the realist view of Maudlin, a few more, okay. And maybe neither. You might say neither. And some, or maybe both. I feel both, okay. Yeah, okay, all right. So there seems to be more or less divided in the operation. I feel people neither and it's a bit less both. And I think I'm trying to go for the both because I think it's, even if you really feel yourself as a realist, you would gain something from trying to understand why it is that you have this other person who has very strong disagreement with you, who presumably is an intelligent person who has thought deeply about these issues. So what exactly did Bell prove in 1964? In the conclusion of his paper, he said, in a theory in which parameters are added to quantum mechanics to determine the results of individual measurements without changing the statistical predictions, there must be a mechanism whereby the setting of one measuring device can influence the reading of another instrument, however remote. And hereby, there is the quantum correlation validated geologic assumptions of predetermination of measurement results and locality. And here he meant that the result of a measurement is unaffected by operations on a distant system, or in other words, by the choices of measurements that you make on this distant system. And what did he prove in 1976? Now he had developed this notion of local causality. And then he said, well, my notion of local causality is that events in one lab should not be causes of events in a space-like separated lab, and vice versa. But this should not mean that the two sets of events should be uncorrelated, because they could have a common cause in the overlap of the backward light cone. And a consequence of this notion of local causality is that then the outcomes in the two labs should have no statistical dependence on one another, nor on the setting of the remote measurements. So here, important distinction is that there's an independence between both, between one outcome in one side and both the setting and the outcome in the distant lab. Given, of course, information about the common causes. And the conclusion then in 1976 is that quantum mechanics gives correlations which cannot be reproduced by a locally causal theory. Okay. Now, in terms of a Minkowski diagram, we have here the two labs, Alice and Bob. There's some choice of setting and an outcome A, some choice of setting and outcome B, and a source C producing your entangled state. And here for illustration, a space like hypersurface. Now, locally causal theory would try to explain these correlations only in terms of causes which travel within the light cone. And so, say if you consider just operational quantum theory without hidden variables, here you have an entangled state. If you know everything there is about the entangled state, these outcomes are still correlated. So trivially, operational quantum theory violates local causality. What Bell's 1976 theorem shows is that even if, and it's not an extra assumption, it's, well, let's try to see if there's still a way we can say local causality. Even if you add some extra variables, here, say gamma, alpha, and beta, to try to reproduce the experiments, as long as there is no arrows going across here, then you cannot explain those correlations. What Bell's 1964 theorem says that if these hidden variables are supposed to determine the outcomes of the experiment, then there must be an influence between one setting and an outcome on the other side. Now, in terms of probabilities, and this is really going to be the only slide with equations in my talk, we say that a quantum phenomenon being the observations we make on the world, described by a theory, or here the same, use theory in the same sense as, say, use ontological model. So a phenomenon is described by a theory if the observable probabilities can be reproduced in this form, where here mu of lambda is a distribution over these extra variables given the information about the source. And here it's a probability for the outcomes given the settings, the inputs, and the hidden variables. So these are model probabilities. And of course, here we assume no superdeterminism, that, or sometimes called the free choice assumption, where the probability for the hidden variables do not depend on the settings, but otherwise this is just an identity in the probability theory. Now, with this, we can define the concept of predetermination as being just that these model probabilities are deterministic, they're 0, 1, which it's important to distinguish that from the concept of predictability, which only refers to the observable probabilities being 0 or 1. Predetermination is strictly weaker than predictability, because there are some models which have satisfy predetermination but do not satisfy predictability, for example, Bohr mechanics. And the notion of locality then is that the probabilities for the outcome in one arm of the experiment doesn't depend on the setting on the other arm given the hidden variables, which is strictly stronger than the notion of signal locality, which is that refers only to the observable probabilities, and vice versa for the other arm, of course. Here again, we have a model like Bohr mechanics, which does not satisfy locality, but does satisfy signal locality, so these are distinct concepts. So Bell's 1964 theorem can be stated then as there is no theory which reproduces quantum phenomena that satisfies locality and predetermination. Now, another concept of another sort of localistic concept, which is in Bell's 1976 concept of local causality, is that the outcome on one's arm of the experiment does not depend on either of the variables on the other side, and nor on any hidden variables which are not on its in its causal path, on its path-led cone. And then Bell's 1976 theorem says that can replace here locality and predetermination by local causality. There's no theory that reproduces quantum phenomena that satisfies local causality. So that should clear up that at least the terminological dispute. But unfortunately, even after the 76 paper, as soon as Bell defined local causality, he went immediately starting using locality as a synonym for it, even though it was quite different from what he meant in 1964. And started claiming that by locality has always meant local causality, and this was the principle that Einstein held sacred. And here we have then this distinction between the operationalists and realists. The followers of Bell, the realists, state that Bell's theorem says that quantum phenomena are non-local. They choose to emphasize the 76 theorem. But most quantum physicists, as sort of maybe evidenced by the loophole-free experiment paper, only know Bell's 1964 theorem and say that we can keep locality if we give up predetermination. So now we try to give a formulation of Bell's theorem which at least try to bridge a gap between those two camps in that they can at least agree on the terms that are used for the formulation. And also maybe realize that there are things that, the more things that they need to give up by looking at this at another kind of formulation, or there's more new fields of research that are opened by considering a different way of looking at Bell's theorem. So to motivate the rest of the talk, then let me look at this quote from Bell. He said, "For me, then, this is the real problem with quantum theory, the apparently essential conflict between any sharp formulation and fundamental relativity. That is to say, we have an apparent incompatibility at the deepest level between the two fundamental pillars of contemporary theory. It may be that a real synthesis of quantum and relativity theory requires not just technical developments, but radical conceptual renewal. And the point of view that we take in this talk is that this conceptual renewal, at least part of it, it's about causality. That Bell's theorem is best understood as being about the constraints from causal structure to probabilities, and not about locality as such. Relativity comes in just merely to supply the causal structure, so to speak. And Bell, of course, was very concerned about these questions of causality, but about particularly falling back on no signaling, he said that we have to fall back on no signaling fast and light as the fundamental expression of causal structure in contemporary physics. This is hard for me to accept. For one thing, we have lost the idea that correlations can be explained. So then what does it take to explain correlations? Imagine, say, that we have a rare virus infection that was simultaneously spread around Brazil and Australia. And some epidemiologists are trying to explain what's going on. They're probably going to entertain three possibilities. Either the virus was carried from Australia to Brazil, or it was carried from Brazil to Australia, or it was carried to both from some third country. That intuition is encapsulated by a principle called Reichenbach's principle of common cause, which says that if two events are correlated, then either one is a cause of the other, or they share a common cause that explains the correlation, that in fact factorizes the probabilities for. So, and it's a fundamental principle in many areas of science, like, for example, say, medical research or causal discovery algorithms. But it leads to Bell's theorem, as I'm going to show soon, and to a contradiction in quantum theory, so it has to be given up. And curiously, Reichenbach actually thought very deeply about quantum mechanics. He formulated this principle in a book called Philosophic Foundations of Quantum Mechanics, published in 1944. So he thought very deeply about quantum mechanics and about questions of causality in quantum mechanics. And he formulated that principle that turns out to be violated by quantum mechanics, but he didn't even notice that. So I think that goes to show how deep Bell's intuition really was. Even someone who thought very deeply about those questions didn't come to Bell's theorem before him. So now to get to this reformulation then of Bell's theorem, let's go back to basics. And we start with some axioms, and they're not meant to be sort of you can't question them. Just that usually they are implicit in any formulation of Bell's theorem. But definitely you can question them, and you should. The first is macro reality, that in any individual run, exactly one outcome and exactly A and B really happen, and they're not relative to anything. So that would say rule out relational quantum mechanics, for example, of many worlds. Another is Minkowski spacetime. Concepts like cones, space-like separated, etc., can be unambiguously applied in ordinary laboratory situations. That doesn't rule out general relativity, but does rule out, say, closed time-like curves, called causal loops. Axiom 3 is an error of time, causal error of time. A cause can only be in the past of its effects. And here, when we have yellow terms, they're meant to be undefined until another axiom or postulate defines them. So here, cause and past are undefined. And our first postulate, and here we're distinguishing postulates and principles from axioms because they will be explicitly stated in the formulation of the theorem. First postulate is relativistic causality, which says that here in axiom 3, the past is to be understood as the past-like cone. Okay. Now, we'll put a few principles that an operationist would be happy with formulating. So the first is the principle of agent causation. If an event A is statistically dependent on a freely chosen action B, again here this is left undefined, then B is a cause of A. So from this principle, we can now form the following lemma: relativistic causality plus agent causation imply locality and no superdeterminism, where now here by locality we mean that the probability of an observable event A is unchanged by conditioning on a space-like separated free choice, even if it's already conditioned on all the events, as long as they're not in the future-like corner, as long as they cannot be possible effects of B. And no superdeterminism just means that any free choices subsequent to some space-like hypersurface are uncorrelated with events on that space-like hypersurface. How much time do I have? 10 minutes. Okay. And remember, this notion of locality is respected by orthodox quantum mechanics. Now, a principle of predetermination can be defined as for any observable event A and any space-like hypersurface S prior to it, A has causes on S, which together with any free choices after this S determine A. And so Bell's 1964 theorem can now be formulated as the conjunction of relativistic causality, agent causation, and predetermination is violated by quantum phenomena. Now the realists, let's say here Bell, would maybe react to this formulation saying to use agent causation as the fundamental causal constant in contemporary theoretical physics is hard for me to accept. For one thing, we lost the idea that correlations must be explained. That's sort of paraphrasing the previous quote from Bell. And more importantly, it's desperately vague, immediately provoking the question, what is an agent? And also, predetermination is sacrificial. It's too strong. It's too easy to give up. And that's important for the operationist to understand. Okay, now for a set of principles that a realist would be happy with. We start with the Reichenbach's principle that says that if two events A and B are correlated, then either one is a cause of the other, or they share a common cause such that conditioning on that cause eliminates the correlation. And now relativistic causality plus Reichenbach's principle implies local causality, where now local causality is if two space-like separated events A and B are correlated, then there is an event C in the common causal past, such that conditioning on C eliminates the correlation. And now with the principle of free choice, we just said a freely chosen action has no causes, or it could just be has no relevant causes in the causal model you're considering. Then we can formulate Bell's 1976 theorem as the violation of the conjunction of relativistic causality, Reichenbach's principle, and free choice, or a contradiction between that and quantum phenomena. Now, for realists, it's relativistic causality that has to be sacrificed because they think that Reichenbach's principle is very important. So it's an important part of what a scientific explanation is trying to do to explain the correlations. And now maybe an operationist, and here I'm using Chaslov, and he might object to putting words in his mouth, but sorry, just as a token operationist. He would say that I find Reichenbach's principle too strong as a fundamental notion of causation. Why should all correlations in nature be explicable in the way that they are in classical physics? Is that fair enough? Okay. Also, how can you realists criticize us for having an agent-centric notion of causation when you still need to assume free choice, which is agent-centric too? All right. So here's our reconciliation version of Bell's theorem, and the key is to get Reichenbach's principle and to break it into two different principles. One which is just a principle of common cause as such, which just says that two events A and B are correlated, then either one's a cause of the other, or they have a common cause that explains the correlation. And we leave open what explains is supposed to mean. And the next principle then tells us what an explanation is supposed to do, and to get to Reichenbach's principle, it's supposed to be such that conditioning on this common cause, you eliminate the correlation. So Reichenbach's principle requires not only that there is a common cause, but that common cause decorrelates the two events. In other words, it explains both events individually. It explains the correlation by virtue of explaining the two events. And so now we can sort of have a diagram of all of these different assumptions that I've been talking about. Here, in the next few slides, the boxes which have bold letters are the principles which are the basic principles on that particular formulation. The colored ones are principles which can be considered in that formulation. And the black ones, it's not very easy to see here, are assumptions which are dropped in that formulation. So here then Bell's theorem can be reformulated as a conjunction of these four assumptions. And the arrows mean, say for example here, Reichenbach's principle, that if there's two arrows coming to a box, it means that the conjunction of these two assumptions where the arrows come from imply that. So common causes and decorrelating explanation imply Reichenbach's principle. Say relativistic causality and Reichenbach's principle implies local causality and so on. So yes, the conjunction of these four assumptions then leads to a contradiction with quantum phenomena, and so we have to drop one of them. Now, what would be in this language? What would be the original realist version of Bell's theorem, the 1976 one? It would be assuming no superdeterminism and local causality, and arriving at a contradiction with quantum phenomena. And the realist would then drop local causality. There were some other intermediate versions, but I won't have time to talk about that, so I'll skip. Now, the new realist version then would have these four assumptions, and they would drop relativistic causality as a consequence, because they would still think that Reichenbach's principle is an important principle to uphold. The original operationist version, the 1964, would have no superdeterminism, locality, and predetermination as assumptions, and implying a contradiction with quantum phenomena. And here, the operationists would drop predetermination. And then here's why it's very important to then, here's a lesson that the operationist has gained from considering the other point of view on Bell's theorem. If you just do that, you don't face up to the fact that there is actually other things, more fundamental principles that you have to drop to accommodate Bell's theorem. Just dropping predetermination is not enough. You have to drop this principle of common cause. And the operationist would say, okay, fine, and given that you can sort of break it down in this way, I would choose to drop this decorrelating explanation. Okay, so just taking stock of so far, we see that there are actually two Bell's theorems, the 1964 and 76 ones, with essentially the same proof, but with different sets of assumptions. And it turns out that the 64 is sort of favored by the operationists and the 76 by realists. And by considering these notions of causation, we can understand why they disagree and find a form of Bell's theorem in which they can both agree at least upon the formulation of the theorem, but just disagree on what assumptions to drop. But still we have to give up something that's important. Some of the axioms like macro reality, Minkowski spacetime, the causal lateral time, freedom of choice, or some of these principles of postulated have been explicitly stated, relativistic causality, the common cause principle, or the correlating explanation. Now, going further, well, either way, the universe is profoundly strange, but going further now, so as I was saying, there's a gain for the operationists from considering another formulation of Bell's theorem, which is that just giving up redeterminism isn't enough, that you have to modify this principle of Reichenbach. And also just giving it up is not enough, because if you get a book like the Book of Pearl, which talks about causal networks, and that goes back to what Martin was talking about in his talk, it's an important assumption in that theory of causal inference, this principle of Reichenbach's principle. So what do we do with this book now, which is widely used in many areas of science? Just throw it in the garbage. No, you have to replace it with something. And there's been some very interesting developments lately in that direction. Very interesting papers, one by Joe Hansen and my co-author Ray Lau, on this, Matt Pusey, and also by Jacques Pienat and Czeslaw Bruckner. And they both provide just this, a generalization of Reichenbach's principle, and much more than that, in fact, but in particular, a generalization of Reichenbach's principle, or at least it can be interpreted that way, that accommodates the quantum correlations and also reduces the appropriate causal classical limit. They do more than that, but I won't have time to talk about it. But the operations now could go say, okay, there you go. We rose to the challenge, case closed for Bell's theorem. It's not a mystery for us anymore. And here I would say, it paid for the operationists to consider the realist point of view once, so maybe we would do the same again. So there's still some cause for concern. Reichenbach's principle could be seen as a consequence of a more general principle that we could call causal completeness. We could say like this: an event is independent of any events not among its effects, given its causes. And Pienat and Bruckner, they propose this quantum causality condition where an outcome is independent of all settings that are not its causes and all outcomes that do not share a common cause. And meanwhile, in the other paper from Hansen and Wall, they require the notion of observed and unobserved events. So I'm saying, those are very interesting papers, very interesting theories, very good developments, but there's still this lingering notions of outcomes and settings, and observed and unobserved. And what would a realist like Bell say to that? I presume he would say something like this: settings, outcomes, who do we think we are? This is a famous quote by Bell. More importantly, the no signaling notion rests on concepts which are desperately vague. The assertion that we cannot signal faster than light immediately provokes the questions: who do we think we are? We who can make measurements, manipulate external fields. Do we include chemists or only physicists, plants or only animals, pocket calculators or only mainframe computers? So he was getting at the measurement problem. So in a sense, one way of seeing the conclusion of this is that so these developments that have culminated with this work from Pienat, Bruckner, and Hansen and others might have reduced, at least from an operationalist point of view, reduced the mystery of Bell's theorem to the mystery of the measurement problem. But to just stop there and think now there is no problem would be maybe the same mistake as the operationalist is stopping at 1964 and not looking at Bell and saying, wait, he has something to say there. So then our question is, why do we need these agent-centric notions of causation when talking about causation in the context of quantum mechanics? Is it a necessary fact, or can it be accommodated? Can we somehow go around that? And maybe that goes back to the question of: are these concepts emergent from some more fundamental theory in which they don't exist? So I think these are the speculations that are interesting to think about. Thank you.